Hello all. So unfortunately we can't get everything done with 2 snow days and not just 1 snow day. So we need to watch a little video and hopefully this is all that we'll need to do. But I'm going to get us started on integration and review just 252 integrals, and then we'll do 254 integrals on Wednesday and Thursday. And we might need to do another video lecture over the weekend to make up for this. But this one will be shorter. So what is integration? We've done derivatives with multivariable functions. Now we're going to talk about integrals with multivariable functions. But to talk about integrals with multivariable functions, we need to know what integration is. So the key idea that we have to remember is that an integral is not an area, it's not an antiderivative. An integral is a sum. It's a sum of little pieces of stuff. That would be my baby. I'm sorry. We'll keep going though. So it's a sum of little pieces of stuff. So in 252, you might have added up areas of rectangles to get area under curve. Or you might have added up surface area of a volume of revolution to get the surface area of a volume of revolution. Or you might have added up little pieces of work to get the total work, to say pump water out of a tank. You might have added up little pieces of volume. You might have added up numbers in sequences and series. You might have added up changes in position. But what you did was you subdivided something into little pieces and then added up. So the big question that you have to ask yourself when you're saying, what does this integral represent? The big question you ask is, what am I adding up? So I'm going to do an example, a 252 example, and then we're going to generalize this into the multivariable setting. And the example is, how much chocolate is on a thin 3-inch long cookie where the linear density of chocolate on the cookie is given by, I'm going to use sigma instead of rho because rho is reserved for something else later on. So the linear density is given by sigma of x is equal to x squared over 16 plus 1 grams per inch, where x is inches along the cookie. So this is the example we're going to work with. And this is why we have a picture of Pocky Sticks, really thin, long, linear-like cookies, so we can talk about a linear density. In 252, you did this with like a thin metal rod or something. So I'm going to do chocolate on along the line, essentially, a thin, long cookie. And so what we do to use an integral, what we do first is we chop up the inputs. Oh yeah, and let's talk about why we need an integral. I can't just take this density function and multiply it by my 3 inches because my density changes depending on where I'm at along the cookie. So I can't just take the density in grams per inch times the 3 inches because my density is different depending on where I'm at along the cookie. So what I'm going to do instead is I'm going to chop up the inputs. So first I'll draw a picture. And here is my picture of my 3-inch long cookie. It's thin and narrow. And I'm going to chop up the inputs into, say, in subdivisions. And if you remember doing this in 252, you wound up labeling things like x0 here and x in here, and x1 was a little past x0, and you'd call a little subinterval delta x. You know, maybe you were in the middle, x sub I and x sub I plus 1. And so I draw a picture and I chop up the inputs. The next thing I do is I calculate the amount, in this case of chocolate, on a small piece. So, amount of chocolate on the ith piece. So that little subinterval there, somewhere in the middle. And the piece here that allows me to do this is I get to assume the density is constant on such a small piece. So that's like in 252 when you assumed that the area under the curve was a rectangle. So you were assuming the height of that rectangle was constant because this piece was so small. And then when you let the number of subdivisions go to infinity and delta x go to 0, it didn't matter that it's not really constant. So I'm going to assume it's constant on such a small piece. And so I'll, at the x sub ith piece, I'll look at what the density is on, say, a left input of that piece. I could do left or right, it doesn't matter. So left or right Riemann sum. And then that gives me the chocolate on the ith piece by taking that constant density times how long the piece is. So it's how many grams per inch of chocolate there is at x sub I times the length of the piece, which is delta x inches. So that gives me sigma x sub I delta x grams of chocolate. In other words, I take that input, square it, divide it by 16, add 1, and then multiply it by delta x. And that's the amount of chocolate on the ith piece. What I'm going to do next is I'm going to add up all the grams of chocolate on all the pieces. So that gives me the sum of the amount of chocolate on all the small pieces. And I'm going to let I go from 1 to n, and that will give me grams of chocolate on like the first little piece plus the second little piece plus the third little piece and so on until I add up all the pieces. And then if I take the limit as n goes to infinity, so delta x goes to 0. This is a Riemann sum, so I get a definite integral. The integral of x squared over 16 plus 1, my delta x, well, as it goes to 0, I call it dx. And I don't want to leave the dx off of my integrals anymore because it's going to matter a lot in this class. So I'm adding up each of these little grams of chocolate for each piece, and I do that from 0 to 3 and that will give me the total amount of chocolate. And once I have it written as a definite integral, I don't need to do a Riemann sum. I can use the fundamental theorem of calculus to evaluate this. So I'm going to use the fundamental theorem of calculus part 2 to evaluate, which says I can find this sum using the change in antiderivatives, which means the total amount of chocolate is going to be x cubed over 3 times 16 plus x from 0 to 3, which is 3 cubed over 48 plus 3 minus 0 cubed over 48 plus 3, which becomes 27 over 48 plus 3. And I'm pretty sure if you add that, you'll get 57 over 16. So approximately 3.56 grams of chocolate on this cookie. And that idea, where I chop up the inputs and then I calculate the amount of chocolate on a small piece, I add it up, and then turn it into an integral by taking the limit as n goes to infinity and use the fundamental theorem of calculus to evaluate, is a process that we're going to keep using to see what we're going to do with integrals in the multivariable setting.